Hello, hello, hello. Can you hear me? Hello. Hi, Aditya. Hi. Nitin Chang. Hi. Hi, Anirudh. Hi. Hi. Okay, guys, let's wait for 5 more minutes. Hi, Ashwin. No, no, we don't need any software today. We are gonna be seeing only theoretical thing. Hi, Vivek. How are you guys doing? Are you all good? Are you all fine? Do you guys know what RL is? Like, do you have a little bit idea about what RL is? Like, do you guys know what ML is actually? So you guys know about ML. So RL is part of ML. Okay, no need to worry. You're gonna learn all about RL today. Okay, let's wait for 2 more minutes, then we will start. Yeah, I think good, good, good. You don't need any prerequisites. Like, nah, you don't need anything. I have started from scratch. It's pretty basic. Oh, okay. What happened? 1 minute, guys. Yeah. Okay. Let's start, guys. Hello, I'm Hariyasudan. I'm from Electrical Engineering Department here at IIT Madras. So I'm the coordinator of iBot Club. I'm also one of the coordinators. Today we are going to see about reinforcement learning or RL. It's a part of ML. Okay. Before going to reinforcement learning, let me start with a Kuti story. Okay. It was in the mid 1940s. There was this guy called B.F. Skinner. Okay. He he had a peculiar idea. Like on the time there were no guided missiles. Like missiles would miss targets constantly due to bad weather condition or like satellite interference or like anti-aircraft guns. So he had an idea. What if something would steer inside the missiles? So he thought of like uh, what would a, a what would happen if a pigeon could sit inside the cockpit of the missile and steer itself. So he built something beautiful. Like think of it as a missile. So this you could see this nose cone, right? You could see the tip of this, right? So inside the nose cone of a missile, he put a pigeon inside it, and he had a screen with pneumatic sensors. And if it was off center, if the target was off center, the pigeon would peck on it, which would make the pneumatic sensors go off, and the missile's fin would adjust itself accordingly to center the target again. It was actually working good, but like the defense department didn't agree that their fate should sit on a pigeon, so they disregarded it. There is a beautiful thing in which how he trained the pigeons. Like he simulated all the environment, like all the turbulences, all the noises, all the heat that would like you would face sitting inside a missile. He trained it. He simulated an exact environment, and screen inside the he put a pigeon inside the cage, and he put a screen in front of it, and he displayed targets which are off center, and he let the pigeons peck at it. And if the pigeons correctly peck at the target, he would drop a single piece of grain to the pigeon. So he's like positively reinforcing the pigeon to hit at the targets. the pigeon itself understood if it pecks at the target, it could get some reward. So the pigeons are actually very fast. Like it would do like 5 pecks per second, which is really pretty fast, right? So this was the early stages of reinforcement learning. This is one of the biological examples of reinforcement learning. So shall we start now? Yeah, pigeons, poor pigeons. That's also a reason why they disregarded it. Oh, is it lagging? Is it lagging? Hello, can you guys hear me, right? Oh, it's fine. Okay, okay, a little bit. You guys know what AI is, right? What an AI is? Hello, guys. Yeah, you guys know what AI is? Like AI means artificial intelligence, right? How do you decide whether a machine is intelligent, or like how do you like say a machine or a LLM is intelligent? How do you say a machine is intelligent? Do you guys have any idea like how a machine is considered intelligent? Gives original ideas. Yeah, that's also a factor. Uh, do you guys know Alan Turing? There is this movie called The Imitation Game. Have you guys watched it? Uh, Repeat the question. Do you know what an AI is? How a machine is considered intelligent? Have you have watched The Imitation Game? There is a guy called Alan Turing, right? Uh, he he produced a paper called The Turing Test or The Imitation Game. The movie was actually inspired from the paper. Like the Turing Test, it was like you put a person in a room and they chat with the computer, and they don't know whether the other person they are chatting with is a computer or a person. If it is indistinguishable, then you can say that the computer or the machine you have created is intelligent. This laid the foundation for machine learning and all that stuff. He was also the father of computer science. Yeah, yeah, it can make decision on its own. Yeah, cool. Yeah, correct. Okay, shall we start? Yeah, yeah, it correct itself over time. Okay, now like you guys know like why do we need ML? Like why don't we use like traditional programming? Why do we need ML? Do you guys have any idea why do we need ML? So okay, no issues. We like think imagine you're hand coding like hard coding software to detect cat in photos. Like there is a image with lots of objects. You need to like circle the cat. Like you need to find the cat. Okay, what do you do? The first step you don't know about YAML, right? You know like simple coding, right? So what you do is like if the shape is triangular, then it's yours. Then create a if statement inside it. like if it have whiskers, then create an if statement inside it, like about having a tail, and continue like adding a description of its physical appearance, right? Like, yeah, to like write about the physical appearance of a cat, it would take like millions and millions of code, right? Yeah, you are right, Nico. We can't hard code everything. Why we can't hard code it? It is because like even if you write millions and millions of line of code, the debugging process would be a total nightmare, and you can't like write every actions what a cat does, right? So it's like dumb to do things right like that, right? So that's why we use machine learning. So the paradigm shift. Do you guys like know what paradigm shift is? Oh, sir, okay. Paradigm shift, like you have a basic idea around which you build a system. So around you have a built system around this basic idea, but then you realize this basic idea is completely wrong. So you create a basic idea, again build a new system around it. This is called paradigm shift. Like for example, initially people thought every planet revolved around the Earth, but Copernicus proved that wrong. That the solar system was heliocentric. That is, every planet revolved around the Earth. Revolved around the sun. This is a paradigm shift. Like initially, the basic idea was wrong, and the entire max surrounding it was wrong. Then they built a new system, and they created max accordingly, which would like match to our new science. Yeah, whole change in our good, good, correct. Yeah. So in traditional programming, you would give the computer the questions and the data, and you would ask answers, right? The computer would give you answers. But in machine learning, you give the computer question plus answers. It itself calculates the rule. It itself calculates the rule. Then like it adapts and scales to the real world. But like in traditional programming, it fails to adapt to scale to the real world. If there is some noise or some errors in the data, the traditional programming would break completely, and the debugging process is so hectic. Yeah. Do you guys understand now why ML is preferable over traditional programming in certain conditions? Which part do you want to repeat, Mr. Sanjit Kumar? Sanjit Kumar. Should I repeat the paradigm shift once again? The major difference between, yeah. So the traditional programming, you give the questions and data, and you ask for answers. But here you give the questions and answers, and it itself calculates rule. In traditional programming, you have a set of rules, you should follow it, and you should answer the question. But here, you have questions and answers, you yourself follow rules. Is it fine, Rajit Kumar? Okay, let's go on with the next slide. Okay, three pillars of ML. Like as Niku said, like you could give there is supervised learning, unsupervised learning, and reinforcement learning. He said like we need to find patterns and train accordingly, right? What supervised learning does is we give thousands and thousands of images, and we give answers. Like we point out which is cat, it itself forms rules accordingly, and then creates its own set of rules. So like if you feed a new image, it could find cat easily. Unsupervised learning is you only give the data, you don't say anything about it. Like it itself recognizes this pattern, you don't say anything about it, you don't say this is cat. From to take two images, if it sees these two objects are similar, then it would recognize and categorize and group them individually. Now the part we are going to see is reinforcement learning. This is actually reinforcement learning is very good. It's like uh, it's very different from both supervised and unsupervised learning. We don't we don't give questions, we don't give answers. It just randomly tries thousands and thousands of times until it hits its target. So yeah, do you guys have any doubt in these three topics, supervised, unsupervised, and it's just yeah. You don't understand what which part do you don't understand, Nico? No doubts. Okay, let's go to the next slide. Okay, what is RL? What is RL? Uh, from this, uh, you could see that reinforcement learning is a part of machine learning, right? Reinforcement learning, supervised, unsupervised, all are part of machine learning. See, it's a part of machine learning where like AI tries to make its own decisions, and it fails again and again until it reaches target. It's like a trial and error method. But there is a catch. You can't if it's failing, you can't tell why it's failing or how bad it's failing, right? So rectify this. There's a thing called systems, a system of rewards and penalties. uh, what you can't like say this is bad, the computer won't understand like this is bad and how bad this is. So rewards and penalties are there to uh, make the agent understand how bad its current status. So what it does, it gives a number. It gives a number like if it gets plus 100, it realizes, oh okay, I did a good action right now, so I will record it in my database. If I get minus 100, oh no, uh, it's not good, so you shouldn't do this again. Or you want to zoom in the Venn diagram. Okay, one sec. Could you see it more clearly now? What is meant by trial and error learning? Trial and error learning is like you try to do something again and again. Like suppose in cricket you are trying to bowl a perfect ball. In the first attempt you would not know how to bowl, right? So you will learn by throwing the ball and you wouldn't get it until and unless you find a perfect technique to bowl the ball. You will like try bowling. That's what trial and error is like. It's pretty basic. uh, okay, so let's go on with the next slide. Why do we need RL? Like, do you guys have any idea why do we need RL? What is what is the difference between like there are supervised and unsupervised learning, right? Why do we need RL specifically? Saves training timing. It's also a part, but still, yeah. Actually, sometimes even RL takes so much time if it's like stuck in some place, more than supervised and unsupervised learning. Imagine you are going in a maze, and if you're stuck at a certain part, you'll you'll keep on doing infinite loops and you wouldn't come out. So RL may crash sometime. It would take so much time. Why do we need RL? Easy to get information. Mm, okay. Don't have to worry about vast label data sets. Yeah, that's a good time. We don't need to feed data. It itself gets it data by trial and error. Yeah, good, Nico. Suitable for yeah, correct. Suitable for dynamic environment. Yeah. So let's see. If you're trying to train a puppy, you guys are trying to train a puppy like by training, you can't like program a puppy's brain, right? You can't like go open the puppy skull and type sit in it. So what we do is, if you say sit and the puppy like tries to do many different action, and if it sits accidentally, you give it a reward. So inside the puppy's thought process, it thinks like, if I sit, I'm getting reward, so sitting is a good thing. Okay. Now what if it chews on your shoes or something like that? You like say no or shout at it. Then puppy realizes, you shouldn't do this. If I do this, I'm getting scolded. So it is not a good thing. So we are positively and negatively reinforcing the puppy to do what we want. We are training the puppy by positive and negative reinforcement. This is what RL is about. You guys understand this, right? Yeah, shall we move on to the next topic? Yeah, okay, let's go. Okay, now from puppy, let's directly transfer this to max. So the RL mainly has four major thing of RL is the agent, the environment, the reward, and the action. So here in the puppy analogy, the agent is the puppy, the environment is the place where we train the puppy, the reward is is the uh, is the treat or the scolding, either the positive or negative reward. Here the action is to sit, or if you throw a frisbee, it catches and comes. That's also an action. So these are all the four main thing of RL. Okay, now let's go to anatomy of an RL. So what happens at each time step? Like now suppose like you are in a particular maze and you need to solve this maze and get out of here. At each time step, what happens? What happens in the brain of the agent? Like at time step t, you are at state s of t. Imagine you're at state s of t and you perform an action a of t on the environment. You perform an action a of t on the environment, so you get a reward r of t plus 1, and you move on to a state s of t plus 1. You guys may have a question why reward is r of t plus 1, uh, right? Because it is r of t plus 1 because you get reward after going to the state s of t plus 1. After reaching s of t plus 1, you get the reward r. So it is r of t plus 1. So this is what happens at each time step in RL. The agent performs an action A of t at state S of t on the environment to move on to the state S of t plus 1 and receives a reward R of t plus 1. Are you guys clear? Okay, shall we move on? How to choose an environment? It's you can't choose an environment. It's the question itself. You don't give the question, you get the environment. See, I told you like we would feed the question, right? Like we would feed the question to the an agent or bot, right? The here the question is the environment, and you have a goal to reach. What do you mean by a state? So what a state is, uh, for example, in a take, think of a maze, think of a maze, and you are at a particular position, right? You are at a crossing state. You can move either left or move right. So what do you do? This position is state s of t, and if you go right, it becomes s of t plus 1, or if you go left, it becomes state s of t plus 1. Yeah, do you guys understand? Okay. Let's see what some important terminologies in RLR. Okay. You guys know what an agent is, right? It's the entity that you're trying to build or train. Environment is the place where the agent trains and interacts. State, it's the representation of the current situation. Reward is the feedback. Yeah. Action, it's the decision that the agent. takes to move from one state to another. Transition. Now, transition is the new thing, right? When agents move from one state to the next state, from S of t to S of t plus 1, this is called a transition. You guys understand, right? And what observation is. So this is a tricky thing. See, you guys are in state S of t and S of t plus 1. From an outside viewer, we can say the bot is at S of t and S of t plus 1. But for a bot to recognize, but for an agent to perceive it, it should use its sensor, right? It's a perception, so it can't always be 100% accurate. Like there may be some errors, and there may be some errors, right? So this is what observation is. Observation is not the same as like uh, doesn't reveal the 100% information. Like you won't be sure whether you are in this state or not, but you are the bot thinks it's in this state. State space is a set of all possible state. Yeah, action space is set of all possible actions. Do you guys have any doubt? Like, do I need to say again about observation? State space. See, I told you, right? You are at a state S of t, and you move on to S of t plus 1. All these S of t plus 1 set of all these states are state space. Do you guys have any doubt? Ah, yeah, we are going to have a little implementation, but like I can show you the code stuff, but you guys won't understand it. I'll show you the output. I'll show you the output, guys. Example of action space. Like take in the case of puppy. The puppy could sit or the puppy could chew shoes, right? These are all the examples of state action. Which part should I explain once more? Should I explain the observation part? Ah, okay. See, what observation is, uh, it's how the agent perceives the environment. It's not the actual truth. It may be the truth, or it may not be the truth. It is how the agent perceives it. So it may not be 100% accurate. It may contain some errors. The agent may think it is in some state A. It might be in state B. The agent can't be sure, but it thinks it's in state B and continue. It thinks it's in state B and continues to move on. Yeah, I will. Yeah, these guys are so irritating, right? Shall I move on? Okay. So now we got to the interesting topic, policy. See, policy is nothing but like it's a strategy or a plan. You need a strategy to move from one place to another, right? Every agent has a policy or a plan or a strategy to move from one place to another. Initially, you have no strategy. This rule book is completely blank because you don't know what the environment is, right? So after failing thousands and thousands of time, the agent creates an optimal policy by which it can succeed its goal. So after each and every state, it updates its rule book. From moving from S of t to S of t plus 1, it updates its rule book. If it gets according whether it gets positive or negative rewards. And there are generally two types of policies: deterministic and stochastic policies. And policy is also written as the Greek letter pi. So shall I move on? Yeah, sure, Pragdish. Where does it save all these policies? And yeah, we have to. We like where do we need to save this like calculating policy or all some complicated stuff. I'll give you a little insight about it. See, uh, deterministic policy is straightforward. Like it's like if you see this state, you need to perform this action. Like if the traffic light is red, you need to press the brakes. It's very simple. Okay, it's very straightforward. It's a direct mapping. So deterministic policy is very simple. Like you can't use this everywhere. Generally deterministic policy is used when we know every rules of the environment. Like in a game of chess, we use deterministic policies. Like absolute supercomputers use deterministic policies, but human ourselves can't use deterministic policies because we can't know all the possible combination, right? So human use something called stochastic policy to play chess, while supercomputers use deterministic policies to play chess. Then they know that there is an absolutely best policy which gives them the best move for their current state. Are you guys clear what a determinist policy is? Little bit. Okay, let me like see. Suppose you're playing with a supercomputer against a supercomputer in chess. Like there's some stockfish kind of supercomputer, right? They would absolutely choose the best option. They would have played chess thousands and thousands of time and would analyze this. Like from a particular state, they would have moved millions of time and find the absolutely best possible choice. That's what deterministic policy is. From this state, you perform action A of T. There is no other best action than this. This is what deterministic policy is. It is the absolutely best action you could perform at this state to move to the next state. Are you clear now? You asked where all these policies are saved, right? See, we create neural networks to calculate and save these policies. It's a like a deeper understanding. Yeah. Okay. Now stochastic policy. I said like people like us use stochastic policy, right? You don't know like we have stochastic policies deals with probabilities. You have a list of action and each has action has a certain probability. You do not know which is the absolutely best option, and you won't do it. You use probability. So it's like in a game of rock paper scissors, if we use deterministic policy, you would always throw rock, and it's easier for the opposition player to like throw paper and win against you because you will always throw rock, right? So here situations like this is where stochastic policy come into play. So what they do is they each rock paper scissors have a probability of exactly 1 by 3. This makes the stochastic polity completely unpredictable and unexploitable. See, it's also like sometimes useful. The rewards, then if you move from s of t to s of t plus 1, the reward might be less. But if you move from s of t plus 1 to s of t plus 2, by following this path, you would get an absolute banger of result. Like you could like terminate you could actually finish the you could reach your goal or something like that. So it might not always be the best path, but you could find the bestest possible path using stochastic policy. It's like it's you can see like p of a bar s. It's like probability of taking action given that the agent is at state. Yes. It's like Bayes theorem kind of stuff. You guys understand what stochastic policy is? Okay. Now, the difference between deterministic and stochastic. As I already said, deterministic has only one single choice. Here it has a list of actions and with their respective probabilities. Here standard formulas AF by FS. Here it's probability of A bar S. And it's suitable for predictable environments. Here it's suitable for unpredictable setups. See, for predictable environments, we could calculate all possible actions and see for which one the reward is more. So we use deterministic policy in such cases. For stochastic, we use where the environment is not so predictable or not so well known. There we use stochastic policies. Now, uh, okay, deterministic is always consistent. It always gives the same result. It always has the same reward. And a stochastic, it gives different rewards for different times. It may also give best hidden alternatives. It may give some good alternatives. Shall I move on to the next slide? Guys, don't type random shit, please. Okay, let's move on to the next slide. Okay, now let's see what is expected return. See, this is a cool thing. Like, it's actually it's a cumulative sum of all the rewards, but from next state reward to the state after that, there is a the priority is discounted. Like it's like the relative value of the next reward is less than than that of the current reward. This is because like rewards, uh, you may not like reach till the final position, right? Your bot may fail current, your bot may fail now, right? So you need not give equal importance to all the rewards. So we introduce a new parameter called gamma, the discount factor, which gives importance to the current state rather than the following states. It keeps on decreasing the importance of the future state. But we also take into account of the future state. We do not disregard them. We just give them less importance. Do you guys understand? So this is what expected return is. Shall I move on? Yeah. See, now we enter into crucial concepts. What is a value function? So what is a value function and why do we need value function? Value function is used to evaluate a state. So when a policy takes action, the val it determines how well or how good a state is, how good the current state is. Like it calculates the rewards from this state to the end till the final state using the expected return. So it could see how well the state is, how good the state is. Overcoming short-sightedness. Like you should also like not disregard the final rewards. I said so, right? In chess, this is very important concept. Like you may like sacrifice some pieces to win the game, right? Like you may there is something called the queen's gambit and thing, right? You may sacrifice a queen or some valuable pieces to gain upper hand over your opponent. So value function is used for this. Like you may also see the future rewards, which helps you that even though the immediate reward is not so good, the future reward is very much bigger than the future reward of other all cases. So value function is very important. So let's mathematically dwell into what value function is. There are generally two types of value function. Even though we call state value as state, we generally state value function we think of state value, and action value we call it as q function. So if someone says value function, you should think about state value, And if they say Q value, you should think about action value. Now let's see what the state value is. You could see from this formula, like V of s equals E pi of G of t, given at the current state. It's like uh, let's talk about the e pi term later. It's like the weighted average. If you have a list of probabilities, then you would like need to talk about e pi. Now it's not a problem. In deterministic, it doesn't matter, right? E pi, there is, since there is only one action, E pi becomes one. So the value is naturally the expected return, right? You guys understand state value, right? Like state value like doesn't give us much intuition, like doesn't give us much input about, it gives how good the current status, but it does not say like how good my next state will be. That's where the action value comes in place. Like it is the value function, but uh, you are at a state and you perform action A. What would be the reward for it and the future reward for it? It is the expected return, given that at the current state you perform an action A of t. You guys understand, right? If you are Python snippets. What do you mean Python snippets? Like, do you want like execution of this? Yeah, okay. Let's go to the next slide. I told you, right? Stochastic policy is like little different from deterministic. Like you need to calculate the weighted average of all these paths. Like here, this formula you could see like e pi. This e pi comes into role here. This e pi is directly the probability. You just multiply the probability with the q values. Q values are the expected returns. That's what how you handle the stochastic policy. Like uh, I'll give you some examples. I'll give you some examples. We'll solve one or two problems about it. Like, shall we solve a problem now, or shall we solve later? Are you guys on with solving a problem now? Okay, let's solve a problem. Okay, you see, yeah, you can see the slide, right? We start at state s of t. We start at S1. There is a 80% probability of moving to state S2 and 20% probability of reaching the terminal state. And you could also like see 60% probability of reaching S4 and 40% probability of reaching S1. So let's try to solve this. Okay, okay, let's try to solve this. So S1. One sec. One second, guys. One second. One second, guys. Sorry for the inconvenience. No, the attendance is not done. One second, guys. Okay, guys. Sorry for the delay. Okay, okay. Now, okay. Now let's try to solve this. So, okay. Now let's try. Uh, what is this? State S1, right? So state S1, and we have a 80% probability of reaching state S2, and 20% probability of state S3, which is the terminal state, right? Terminal state. Uh, and let's see what's the reward is. Uh, what's the reward? So the reward is okay plus 5. Okay, here its reward is minus 10. So the reward here is plus 10. The reward here, sorry, reward here is okay. The reward here is plus 5. Here it's minus 10. And from state S2 we have a 60-40 possibility, right? Sorry, 60%, 60-40, right? 60% and 40%. Let's once again check. 60% of moving, reward is 100, reward 100. Here reward is 0, reward is 0. uh, from here we reach terminal state, and we reach, okay, okay, we reach terminal state here. Yes, 4 terminal state, terminal state, and here we reach. Oh, oh, you can't see my screen. Oh, sorry. Okay, one sec, one sec, one sec, one sec, one sec. What happened? Can't see my screen. Oh, you can see it, right? Is it fine now? Is it fine now? Sorry, 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 sorry. I didn't. Now it's fine, right? You can see now, right? It's fine now, right? Okay, you can see it now, right? Fine. It's fine, right? No, no, no. Yeah. So, sorry, I just wrote the question. See, there is state, there is state S1 here. There is a possible 80% probability for moving to S state S2. From here, there is a 60% probability moving state S4 and 40% for S1. And there is a secondary chance where from 20% probability you directly move to the terminal state. Okay, can you guys say, let me ask a question. Can you guys say what is the value function, like what will be the output value function for the terminal state? Like what would be the value for the terminal state? Take a guess, take a guess. What would be the value for the terminal state? Here we are totally talking about state value. As I have said, value function, generally, if we say value function, it's only about state value. Now, like, think about it. Oh, sorry, you can't see, right? Okay. Now think about it. What would be the value of the terminal state? Do you guys have any idea? No idea? Just guess, guys. Just guess. Just guess random numbers. We are not calculating probability here. We are gonna calculate what are the values of value function of state one and value function of state two. I'm asking you guys what are V of S3 and V of S4. Can you guys say what are values of V of S3 and V of S4? Yeah, based on reward. It's correct. Based on reward. For terminal state, what is the reward? Do you have any reward? Yeah, we need to take the reward consideration. I will explain step by step. Like first, let uh no, no, no. Like, see, for the value function, the formula is e pi into expected return rate at the current state. Yes, this is what we saw, right? Here, the expected return for V of S3, V of S3 or V of S4. What do you guys think would be? What is expected return? Expected return is uh, reward, right? Plus gamma, so on, so on, so on. For the terminal state, what do you think the reward would be? in this oh, in this question I didn't. Do you guys have any idea? Yeah. Uh, the probability is not zero. You are correct, but the value function is zero. The probability is not zero. How can you say the probability is zero? You can't say the probability is zero, right? See, from S3, you can't go to any other thing, right? You understand? From S3, you oh probably sorry. Yeah, it's actually zero because from this is the terminal state. From this state, you can't go to any other state, right? So there would be no t plus one after reaching the terminal state. Am I correct? So it's zero. Do you guys understand why it's zero? Do you guys? Okay, okay. Now see this. We know the value of S3 equals zero, and the value of S4 equals zero, right? Now we need to find S1 and S2. Let's go step by step. We oh shit. Okay, let's go step by step. Okay, now let's see what V of S1 is. V of S1, what is it? There is a 80% probability of going to state 2. Now what we do is 80 by 100 of what is the reward? What is the reward? Reward is plus 5, plus 5, right? Plus uh, plus gamma into we reach state S2, right? We reach state S2, right? So it would be V of state 2. Uh, and also I didn't take the gamma values. One sec. Uh, what are the gamma values? The gamma value is zero point 0.5. Yeah, the gamma value is zero point 0.5. Yeah. What do you want to repeat? Do you want me to repeat why the S3 and S4 reward is zero? Do you guys want to repeat why S3 and S4 thing is zero? Mr. Omkar Sharma, do you want me to repeat? Hello guys. Shall I move on or should I repeat it? Okay. See, here I wrote V of S1 equals 80 by 100 of 5 plus gamma of V of S2. You guys might confuse why I didn't write the next reward and I wrote the value function. So let's talk about this. Suppose what is V of S? V of S is e pi of expected return, right? G of t, right? What is G of t? G of t is nothing but the rewards, right? R of t plus 1 plus gamma of r of t plus 2 plus so on, right? So what do we do now is this is for v of s of t, right? So what do we like now? What do you write for v of s of t plus 1? E pi of g of t plus 1, right? So what do you write here? Here it's e pi of r of t plus 2 plus gamma of r of t plus 3, right? Plus so on. So from here you could see that v of s is v of s. Oh, sorry. Okay, one sec. uh, v of s of t equals r t of plus 1 plus gamma times of gamma times value of s of t plus 1. Can you guys see this? Can you guys understand this? Can you guys understand this? This part. The v of s of t, this part, v of s of t equals r of t plus 1 plus gamma of v of s of t plus 1. You guys can like, you could like write e pi, but it doesn't matter the e pi. You guys need not worry about e pi. It's just the weighted average, right? You could multiply it with the rewards or something. Okay, you understand this, right? See, you can see here, the v of f, there are two value function, but for defining value function we are using value function, right? For defining value function we are using value function. You can see this, right? This is something called recursion. This nature is called recursion. Do you guys have any clue about recursive functions? Do you guys have any clue about recursive function? Oh, you guys know what recursive function is? Good. So for people who don't know what recursive function is, it is a function which calls itself calc factorial. Yeah, kind of. Yeah. You got it. But yeah. See, let me take an example of calc factorial. Like suppose n factorial, right? How do you calculate n factorial? You jump into n minus 1 factorial, right? Like similarly, you will go on, and put into n into n minus 1 into so on. Sorry. Okay. Uh, so on. 1 into 0 factorial, right? How do you define 0 factorial? How is 0 factorial defined? So we know that, sorry, we know that 0 factorial is defined as 1, right? So recursive function is a function which calls itself, and you give a smaller input to the function each and every time to reduce to its base case. Here the base case is 0 factorial. You are trying to reduce this n factorial to 0 factorial. What you are doing is reducing by giving smaller inputs. For example, take this case: t of n equals t of n minus 1 plus 1. Can you guys solve this? Can you guys solve this? Can you guys solve this function? Like, can you guys solve this function and give me the answer? What do you think the answer is? Oh, sorry, I didn't give the base case, right? Sorry, the base case is t of 1 equals 1. Sorry. So we are trying to make whole 1 by calculating the whole thing and set. Yeah, we are like trying to reduce it to the base case. Now what do we do here is, instead of n, I would substitute n minus 1. What would happen? Now see, this is reduced to t of n minus 2 plus 1, right? I will substitute this here. I'll substitute this here. What would happen? T of n equals t of n minus 2 plus 1 plus 1. So t of n equals t of n minus 2 plus 2. You can understand, right? Like it's uh, you are to calculate this function, you are calling this function again with smaller inputs. You're to calculate this function, you are calling this function with smaller inputs, and you also have a base case to converge it to. Yeah, correct. Yeah, AP with common difference 1, yeah. And it's correct, yeah. So the answer would be T of n. T of n equals n. So you guys understand what recursion is, right? Recursion is a function which calls itself with smaller and smaller inputs to converge to the base case. Okay. Now you could see this, right? We You could see that the value function is recursive. You guys could understand the value function is recursive, right? Guys, fine. Okay, let's move on with the problem. So we could see here, like I wrote like 80 by 100. Now you understand why I wrote V of S2, right? Why I wrote V of S2. Okay. Now I need to calculate this 20% probability too, right? So what I'm gonna write is plus plus. Okay, one sec. Plus 20 by 100 of what is the reward? Minus 10. Sorry, minus 10 plus gamma into future reward. We know the future value is 0, right? So we directly write 0 into 0, and this is how we like 80 by 100 is it's like zero point 0.8 into 5 plus what is gamma 0.5 of V of S2 plus zero point 0.2 into minus 10, right? So it's zero point 0.8 into 4 plus zero point 0.4 V of S2 minus 2. So it's nothing but 2 plus 2 plus zero point 0.4 V of S2. Am I clear? I guys find this? You guys are fine with this, right? So we write V of S, oh sorry, V of S1 equals 2 plus zero point 0.4 into V of S2. Now what we do is to calculate V of S2, we are going to calculate V of S2. How are we going to calculate V of S2? V of S2 equals uh, what 60% probability, right? So 60 by 100 into 100, the reward is 100 plus gamma times the terminal state reward is 0, right? So 0 plus 60 by now 40, the reward is 0, 40 by 100 into the discount factor is zero point 0.5, and we reach where do we reach? We reach state 1, right? So we write value of state 1. So now calculate this. 100 cancels. V of S2 equals 60 plus 0.2 V of S1. So we have now we have linear equation in two variables, right? It's easy to solve, right? Okay, you guys got it. You guys got it. How we calculate like functions with stochastic policies? What do we do is take the probability and multiply with expected return. That's it. And sum the probabilities. Like you need to calculate the weighted average of the expected returns. It's like 80%, 80 by 100 into expected return of state 2 plus 20 by 100 into expected return of what this action would provide us with. You guys understand this, right? You guys understand this? You guys understand this? Should I explain it once more? It's fine, guys. Is it fine? What does discount factor, how it's affecting? Yeah, now let's discuss about discount factor. See, why do we need discount factor? That's a good question. We need discount factor to prevent infinite loop. Suppose you're doing an endless task, right? If you don't like, you're doing an endless task, and if you're for moving each step your reward is one, then it would, like, you can't calculate the value function, right? It would keep on going one plus one plus one plus so on. You can't calculate it, right? So we use discount factor. One part of is for math stability, the other part is like, the future is uncertain, right? You may not know when the, you may not know the robot, like, completes its goal or achieve its goal. It may fail at some instant of time, right? Any instant of time actually. So we give priority to immediate rewards rather than future rewards. That's the main role of discount factor. The role of discount factor is to give priority to immediate rewards rather than future rewards. You do not disregard the future rewards, but you still need to give more priority to the immediate rewards. It Okay. Do you guys understand this? Do you guys now know why do we need discount factor? One is for match stability. The other is for to give priority to immediate rewards rather than future rewards. And the other thing is uncertain future. Like, you do not know that the future is going to happen. There is no 100% certainty that the future states will occur or not. Are you clear, Niku? Got it, but what does that 0.5 actually mean? Like, it depends on your model. Like, it's not like 0.5 is the only thing. It should be between 0 to 1. Like, think of it as a GP, right? 1 plus zero point 0.9 plus zero point 0.9 into zero point 0.9. Only then you could add it easily, right? So we need a number between 0 to 1. It can be anything. It can be anything actually. It can be anything. Uh, it depends on how much you value your future reward. If it is 0.9, you value your future reward more, and if it's 0.5, you value your future reward less and lesser. Do you guys, do you understand now? It should be 0 to 1, don't forget that. And also, how much you value your future reward. Is it clear now? Okay, fine. I explained the recursive nature of value function, right? Here we could see it. uh, oh, sorry. Okay, okay. Now now let's go on to value based learning. See, there are two types of learning: policy based and value based. So both policy based and value based has a policy, but the policy for value based is very simple. Like, you not you need you don't need like complex neural networks, which I talked about earlier. Like, in policy based learning, you need very complex neural networks uh, to calculate all the policies and stuff. In value based learning, it's very simple. Like, see, look at a particular state, and you estimate the expected return or the state value. But in value based learning, we uh, mostly calculate. We don't want to see how our current status. We need to see what the next state is going to be. Like, if I perform action A, what the next state is going to be and how the rewards are going to be, and if I perform action B, what the states are going to be and how the reward is going to be. That's what we care about. We don't care about the current state, right? Because we already got the reward for it. We don't care about it. We care about the next state. So we use q values or the action value, I said before. So here it's a very simple policy. It just looks at the q value, and whichever q value is the maximum, it performs that action. And there are some pros and cons to it. Here, the pros are, it's the decision making is very simple. You need not do some complex neural network kind of stuff. And it has an high sample efficiency. uh, it's like, you also have mathematical convergence. I told you, right? You use discount factor for the values, so you always have a like an exact number to give input. You don't have like, uh, there's an exact number to give input, so it's easier. And the cons are, it can't handle continuous action. This is a good thing. See, suppose you're driving an automated car, like you need to steer, right? If you use value based learning, it's so like you can't calculate thousand like there from minus 180 to 180. Suppose your steering wheel ranges from uh minus 180 to 180, right? uh minus 180 to 180, you can't like write q value for each and every degree, right? For point 0.1 degree, or it would be like you would need like infinite amount of space to write all that thing, right? So it's you can't handle continuous action, so it's false. And overestimation bias, this is a what do you say, if you like give the same inputs again and again and again, it would like depend more on the input, like it would mold itself to perform only for that input and not other inputs. If you give a new state to it, it would fail. The main concept of value based learning is you if it encounters a new state, it fails because it doesn't have the q value for it, right? So it doesn't know what to do. There is also some ways to overcome this. I'll talk about it later. Do you guys understand what value-based learning is? It is a policy in which you look at the Q values and choose the action for which the Q value is highest. That's it. That's value-based learning. Do you guys understand it? For a steering wheel, it can be more. Yeah, it can be more than just for a sake of explaining. I said it. Like I'm telling, there can be like thousands and thousands of. You can't calculate Q value for each and every like point 0.1 degree or point 0.1 degree, like it would take infinite amount of space, so it's not like feasible, not possible actually. So let's see what a q table is. See, think of a spreadsheet. You guys know what a excel spreadsheet, right? You have rows and you have columns, right? So think of in rows you guys have all these actions, and in the columns you guys have all the states, and for each state, the for all the actions there is a particular q value. uh, Imagine there's state s1, there's a and there are 4 to 5 options, see 4 to 5 actions. For each and every action for the state there is a q value. Similarly for different states, different actions, there are different q values. So these cells contain the q values. It's like it's just a spreadsheet with states in the column, states in the column and actions in the rows, or vice versa, and the cells representing the q value. You guys understand this? How what is a q table? Yeah, okay. Now let's see how a Q table is formed. This is a good thing, right? You don't know like suppose like you don't know initially what values to give, right? You didn't even go to state S1 and S2 or S3, right? Imagine there are three states, S1, S2, S3. You can't like from start give values to it, right? So how is a Q table formed? Initially we initialize all the values to zeros, then randomly you perform an action, and you get some reward, right? According to this reward, you update your queue table. Again, uh, again you perform all these actions again and again and update your queue table until it's optimized. See, initialize to zeros and you explore randomly. You encounter a reward. What do you do? Update and propagate backward. You see, the way in which we update our queue table is kind of peculiar. Let me like sorry. Let me explain. See. This is also called a Bellman's equation. Let me show you. Q, sorry, okay. Q of S comma A, Q of S comma A plus learning rate into uh, rewards. Oh, sorry. I should write expected return minus Q of S comma. This is the initialized this and this are the initialized value. This is the after encoding you would get the expected return, right? Other you could say the new q value, like the new value. Okay, you guys understand, right? This is how you update the q values. You take this is like you call it temporal difference learning. We need not go into the terms. Let's see. We take the q value and update it with difference in the q value. This is the new q value. This is the new q value. You have seen, right? This is the new q value. That is q of s dash a dash minus q of s a. Old new minus old. We are updating with new minus old, and this alpha is called as learning factor. Learning factor. So we do not want it immediately to copy the entire thing, because as I have said, you may not like there may be some error in it. Like what if the data is error? So if there is an error in the data and we completely copy this, then this would be a problem. Like that's why we introduced a concept called learning factor, that you don't update it directly. We just update the difference of it multiplied by the learning factor. Do you guys understand this? Or should I explain it once again? See, the learning factor is also kind of similar to discount factor, but the the way in which we use it is different. For a learning factor, we use it for like use it to prevent any miscalculations and error, and discount factor is for like the I explained to you guys, right? Okay, okay, I'll explain once again. I'll be clear with it. Forget this, forget this. Initially, it is it is initialized to q of s comma a equals 0. This is the q value. Fine, right? This is fine. Now what I do is I encounter a new state. I encounter a new state. Uh, I encounter a new state with certain rewards and something. So what I do is I'm gonna update this q value plus the learning factor into what I get the new q value. Do you guys, how is this different from discount factor? Yeah, I told you, right? Discount factor is for the rewards. This is for the Q value updation. Both are totally different. You don't, uh, rewards are different from Q value, right? Like, see, learning factor is introduced to not carry on all the miscalculation errors that may have been in the new Q of S comma S dash comma A dash. Like, if you guys are not clear with it, let me clear with an sorry. Let me clear it with an example. See, you could see this, right? Okay. Let me draw stuff here itself. I can't. Okay. Reaching room C is plus 100. You guys see it and like tell to me. Uh, okay. See. So okay. Uh, room A, room B, room C. So the reward is plus 100, and the learning factor is zero point 0.5, and the discount factor is zero point 0.8. Okay. It's okay, right? Now we are gonna draw a Q table. A, B. It's a one-dimensional thing. You go from room one to room B to room C. It's one-dimensional. So it's like you go from A to B to C. So there is only two possible actions, right? Either left or right. So I'm gonna write left or right. So initially I'm gonna initialize all these values to 0. Okay. So from now, suppose I'm at A and I'm going to B, right? If I go to B, I don't get any reward, so I need not calculate the Q value. I need not update it. And from B, suppose I'm going to C. If I go to C, I get a reward of 100. I get a reward of 100. So what do I do? Now I'm gonna update my Q value. What was my initial value? 0, right? Plus my updation is, what is the learning factor? Zero point 0.5 into now I'm gonna calculate my new Q value. How are we gonna calculate new Q value? From state B, I performed the operation right. What do I get? Reward 100. So 100. That's it. It's equals 50. So now instead of this 0, we are getting 50. Okay. Now we perform it again. We perform this action again. From A, we are going B. Now there is a thing. If we go to B, we need now we can look at the future rewards, right? Initially, all the rewards were 0, so we didn't do anything. Now we are gonna look at the future rewards. So from Q of S of A equals initially it was 0 plus the learning factor into the reward is 0, but there is a future reward, right? So I'm gonna put point 0.8 into the future reward is 50, right? 50. Oh, sorry, I forgot to subtract minus 0. Okay, so it's nothing but point 0.5 into point 0.8 into 50. Okay, point 0.8. It's 5. It's like around 20. Yeah, it's 20. Now we update this to 20. Now what happens is, since our learning factors, we know this. See the actual see now, forget every learning factor and all this shit. Now, let's find q values for A and B. Q value A, if I'm performing right action, what would be? Think what would be? And Q B, and performing right. You guys know the formula for Q value, right? Should I write the formula for Q value? Q of S comma A equals see, since value function and Q function are both the same, both are recursive. So it's R of t plus 1 plus gamma of Q of S dash comma A dash. See here, here we are gonna take maximum. See, from state S, we are going to state S dash by performing action A. Sir, please show the QR code for attendance. I'll show after 5 minutes. Uh, so from S, I'm going to S dash right by performing action A. And from this S dash, I should write the maximum Q value containing as the recursive thing, because my thing shouldn't be affected by future. So I'm going to take max of it into account. Do you guys understand this? Like, understand this is the formula for Q. Do you guys understand this? Do you guys understand this? Hello, guys. Should I explain it again? Guys, like go talk. Okay. Let me explain about learning factors. See, I told you guys, like, suppose, like, how to explain it? Okay, learning. Wait. Let me explain why we need learning factor. Oh, you see, can you tell what Q value again is? See, Q value. You guys understand what value function is, right? You guys understand what value function is, right? Smiley. Wait for a second. I'll explain to you what learning factor is. Do you guys understand what? Yeah, you know what achieve, what value function is. So it's similar to value function, but there is a subtle difference. See, a value function tells you how good the current state is, but a Q value tells, like, if you from this state, if you perform this action, what would be your future rewards. It doesn't like give cumulative rewards kind of shit, but like it tells you how good this action is. It's like a numerical thing to say how good your action is. Do you guys understand this? What a Q value is? See, Q of S of A is like after performing action A at the current state, you reach action S dash and you receive a reward R of T plus one, and the further rewards are optimized. It's maximized. Okay, can you guys understand Q? What is a Q value is? Okay, you understand Q value, right? From this, could you calculate me what is Q of A given that you perform right without the learning factor kind of shit? Can you like say what is QB, right? Can you tell me what this is? Like, see, this is the given thing. Room A to room B to room C, and the reward at reaching room C is 100. Okay. Now tell me what Q of A comma right and Q of B comma right is. Can you guys like type like what is the Q A comma A of right and B of right? Are you guys like you could not, or should I do it? Like A to B to C, and the reward at reaching C is 100 plus 100. And the sorry. Oh, reward is going to zero, right? What do you mean the reward is going to zero? I forgot to mention the discount factor. Gamma is 0.8. Okay, you guys calculate this thing. You guys calculate this thing. What do you mean the reward is going zero? For which step? For the step from A to B, the reward is zero. Guys, can I not? Or should I do it? Hello guys. A right will be zero. What would be B right? You can see the formula, right? Q of S is R of T plus 1 plus gamma into Q of S dash comma A dash, and it's maximized. And the what is Q of B, right? It's directly 100. It's directly 100, right? So it's